Hello and welcome to another one of D's ADD videos. Today we're going to look at an optimization word problem example. If you remember, the first step in these problems was for you to read the problem without writing anything down. So here's the problem. We have Farmer Joe has a plot of land that he wants his cows to graze upon. He wants to fence them in. So one side of the plot of land is up against a river and doesn't need any fencing. He has 2,000 feet of fencing, and he wants to know what the dimensions are that will maximize the amount of land for the cows to graze, and just how much of his land is going to be taken up. All right? So, now that we've read it, let's reread it and write down the pertinent information. So we have a plot of land. We know we've got a river. We got to draw a diagram, and hopefully when you're done doing that, you get something that looks somewhat like this. So here's your plot of land. We're going to have a length and a width. And it makes sense to have the length opposing the river, not the width. That way you use your fencing in the best possible manner. You clearly defined your variables at that point. L is the length, W is the width. In this case, it's not as crucial, but in other word problems, when the variables aren't as obvious as they should be, then clearly labeling them always helps. Come up with the two main equations and the constraint. You're going to have A equals L times W, because the amount of land is what we're trying to maximize, right? And the amount of land is measured by area, whereas the fencing goes around the perimeter. You're not going to have fences all throughout the land, right? It's on the outside. Unless Farmer Joe's a little crazy, which he might be. All right, so because one side of the plot of land is against a river, we don't need that side, so it's going to be, instead of 2L plus 2W, it'll just be L plus 2W. So which one of these is the constraint? I already answered that because of the fencing going on the perimeter. That 2,000 feet is your constraint, goes outside. So at this point, we get the area equals L times W is the main equation, and then that's your constraint. So on to step 2. So step 2, we're going to have to solve our constraint for one variable and plug it into the main equation. The reason why is because you don't know how to derive just yet a variable or an equation with two variables. So if I were to do that, L is easier to solve for. I won't have any fractions, so I just subtract the 2W on both sides, and then I plug L in for L in the area equation. Okay, so you see how the constraint helped us eliminate the extra variable. Now this is a one variable equation, and you should be able to derive it. All right, so step 2, derive and find your critical points. So when you do that, you're going to get 2,000 W minus 2W squared becoming 2,000 minus 4W, just bringing that down. Derivative of a number times a constant is just that number. Subtract the 2,000 on both sides, divide by -4, you get W equals 500. Okay? All right. So now that we know that W is 500 and that's our critical point, there's 3 ways you can approach proving it's a maximum. So, first way in doing so is going to be the first derivative test. If you remember the first derivative test, what you do is you draw a number line, put your critical point on there, and you pick a point to the left and the right of the critical point and plug it into your first derivative. If you do that, you don't care about the exact value. You can see that 2,000 minus 4 is greater than 0. So you put a plus sign where I plugged in a 1. Note, because this is a width, you can't pick anything below 1, all right? Because your width has to be some distance. It has to be greater than 0. I guess you could pick a fraction, but why do that to yourself? Just pick 1, nice and easy. And then pick 1,000, 10,000, whatever you want to the right of 500. And when you do that, you'll get a negative answer, less than 0. So I put a minus sign there. Anytime it's a plus, then a minus, it's indicative of a maximum. Okay? So we've proven it a maximum. So if it goes up, then down, local max. Method 2 is a second derivative test. Basically, the second derivative test states that if you take the second derivative, plug in your critical point, it's greater than 0. It's opposite what you would think. You would think greater is a maximum, but it's actually a minimum. And then again, opposite common sense, less than you would think is a minimum, but it's actually a maximum. All right, so if you were to do that, when you take the second derivative, you get negative 4. Well, normally there's a variable for you to plug in, but no variable means that all your critical points behave in the same way. In this case, because it's less than 0, all your critical points are local maxes. All right, we only had 1, but in this case it's a max. So that's what this is saying. No variable, all critical points behave the same. Because it's less than 0, they're maxes. Okay, so these are all doing the same thing. I'm just proving it. I don't know which way your class is doing it. Whichever method is what is being done, stick to it. You can use first derivative test as the actual problem and then second derivative test to check it. That's the way I usually do it. Some courses require you to use the absolute extrema method. In this case, you got to find your endpoints. We know they're measurements, so the width must be greater than 0 and the length must be greater than 0. Well, if the length equals that expression of 2,000 minus 2w, you can make that greater than 0 because the length has to be greater than 0. And when you solve, we get the upper bound of 1,000. All right? Now, the good thing about this method is when you plug in your endpoints, you will get 0, so you don't even really need to plug them in. And then if your answer is above the endpoints, then it's a maximum. If it's below, then it's a minimum. But the problem with this is sometimes it's difficult to find endpoints. All right? So either way, we've proven that that width of 500 is maximal. Pick your poison, whichever method you like. Now we have to conclude it all. In order to conclude it all, we must have a sentence saying the following things. First, we must find the other measure. The width is 500, so to find length, go to where it says L equals. All right? Plug in, you get the corresponding length is 1,000 feet. Then we put it in a sentence form. Dimensions that lead to a maximal area are 500 feet by 1,000 feet. That was a T, I'm sorry, I guess I erased it. And then the max area, because it didn't ask how much land, is 500,000 feet squared. All right? So notice how I concluded it in a nice, concise manner, brought it all together. But the main steps will be for you to draw your diagram, clearly label your variables, come up with your equations, solve your constraint for one variable, plug into the other equation, the main equation. Now that it's in terms of one variable, take the derivative, set it equals 0, find your critical point. Then either use the first derivative test to prove it's maximal, the second derivative test, or the absolute extrema method. All right? I hope I've clarified any confusion that you might have. Practice, practice, practice. As always, thank you and have a nice day.